So welcome everybody to this after lunch session. In the next 3 hours or so, Thomas and I we are going to start giving you an introduction to probabilistic programming languages. Okay. So let me start with a kind of brief overview of which is going to be the plan of this afternoon and also the plan of tomorrow, because the content of this afternoon is going to be highly related to what we are going to show you tomorrow. Okay. So today we are going to see an introduction to probabilistic programming, motivation. So what is probabilistic programming? Why we need probabilistic programming? And we are going to also start to speak about Pyro, which is the probabilistic programming language that we will use to exemplify the power of probabilistic programming languages and also to work with the content that we will see tomorrow in relation to variational inference. Tomorrow, okay, we are going to see variational inference. Before lunch, we will look at classical variational inference. After lunch, we will look at modern variational inference. And in the evening, we will extend a bit more of modern variational inference. And all of this will be done in the context of a probabilistic programming language and more specifically about Pyro. So what we are going to see this afternoon is going to be useful for following the day of tomorrow. Okay? Okay, let me start providing a kind of motivation of probabilistic programming languages. And for motivating the need of probabilistic programming languages, I'm going to start speaking about machine learning system in general. Because at the end, what we really want to do is to create a machine learning system, is to create a solution, okay, that solves problems out there. And the question is like machine learning system, everybody knows nowadays that they are quite useful, quite powerful, but at the end, they are also complex, okay? They are highly technical to be developed, okay, and require usually a big effort. And for this reason, when developing a machine learning system, you need highly qualified experts, okay? So this figure is quite common. So a kind of, kind of people that develop this kind of system need to have a kind of background in computer science, a background in math and statistics, and also kind of knowledge about the specific problem they are working on. Okay, that makes, the need of requiring high qualified experts. And at the same time, because when you are developing a machine learning system in general, okay, we are not really right now talking specifically about probabilistic AI or probabilistic machine learning. Just developing a machine learning system in general, okay, it's also difficult because we need to really, navigate many different options, okay? This is like a cheat sheet from the scikit-learn, a very popular machine learning library where, there are many different possibilities depending on the kind of problem you want to solve. Understanding the trade-offs, the different possibilities, just require knowledge and make it complex. Yeah. And not only that, it's like even if you are able to develop your machine learning model, okay, have a specific model well-trained, well-designed, able to make predictions or able to make any kind of task. When you deploy in a real-world system to solve a real-world task, this piece of code is going to be just a small part, okay, of the whole system, okay? So that means having a machine learning system running, solving a real-world task, it's complex, okay? And the consequence of that is something that we have seen for several years from now, and the trend is completely clear. It's like there is a shortage of AI experts, and it's driving the salaries high, okay, because there is an imbalance between the offer and the demand. And the problem of that is it's happening, okay, that only big corporations are really the ones having the resources to develop machine learning system, okay? And I'm just focusing here in the expertise needed to develop these kind of systems. I'm not just talking about the computational resources that they may need to develop this kind of machine learning system. Just only from this side, okay, there is a bottleneck. The question is especially when machine learning is starting to really take off in the industrial world. It seems to be at the beginning that we were in a kind of similar situation than 50 years ago when computers show up. Okay, when computers show up, some companies, some people really realize that, it was a cool technology that's going to have a lot of potential, okay? And at that time, when people started to use computers, they have to call them, they have to use a low-level programming language, okay? It was really assembly code, okay? And this kind of way of programming computers made to be a very complex task, where only people with a high level of expertise were able to really take a computer and extract and make the task that you need to solve the kind of problem that you wanted to solve. Okay, and the problem of that is the access to this technology was kind of highly restricted to very few corporations. Okay. Fortunately, the things happens, and this is because people started to develop these high-level programming languages that brought a lot of advantages. Because now, when you learn the high-level programming language, you don't have to focus on the low-level hardware details, okay? Because there were another people that they really could focus with the right level of expertise in this kind of low hardware details. They weren't people developing compilers, and that brought big gains in productivity. Okay, suddenly a lot of people were able to code. Okay, and people were able to code very quickly, and this has been a trend that is being keeping in the last 20 years, in the last 40 years since high-level programming languages were developed, and that brought a kind of democratization to the software development. Okay, and this is something that also happened when developing this in the context of machine learning. Okay, and this is because a lot of people, a lot of corporations, they have put a lot of efforts in developing machine learning libraries that have this kind of high-level abstractions, okay? Because by having this high-level abstraction, they really were able to, when you are using this kind of high-level machine learning libraries, you don't have to take care about the low-level details. And that has been one of the main reasons that this technology, machine learning technology, has increased so much the level of adoption. So without the presence of Keras, of TensorFlow, of PyTorch, very few people will be using machine learning, okay? Because it's really tricky to make these things work, to code this kind of algorithms. But thanks to these nice libraries, all people in a few lines of code can set up a neural network, okay? Train the neural network and start to make predictions, okay? That has really helped to democratize the use of this technology, in some sense, okay? The question is and this is the main point now, is which are the high libraries in the context of probabilistic AI? Okay, so which are the high libraries that are going to help us, okay, to code the kind of probabilistic model that Celia showed you today in simple way, without having to spend, months coding or requiring you to have a very high level of expertise, just, having the basic notions and be able to start playing around. Okay, so the high-level libraries in the context of probabilistic AI are probabilistic programming languages. Okay, this is the high-level libraries in this context. And the nice thing of these libraries is they have this kind of a stack architecture. Okay, so it's here are supposed to be the domain expert, people with a specific problem that they want to apply probabilistic AI methods in order to solve their problem, like analyzing my biological data, okay, or any kind of problem I have. And then, then all these guys will use a probabilistic programming language, which use the same language to code their models and try to solve their problems. And then down here in the next layer, we will have in this layer, we will have the machine learning experts, okay, that we will develop the machine learning algorithms, the machine learning solvers that in our case is going to be, and you will see that in the rest of the week, just how to implement inference in a probabilistic model. And then we will have another layer where, we'll be the compiler experts, where we just, implement all this stuff, and at the end, we are going to, being able also to run it on top of the specific specialized hardware. So we have a stack architecture similar to the kind of stack architecture that appears in regular standard machine learning libraries, specifically in the context of deep learning. Well, the benefits of the probabilistic programming languages are going to be we are going to be able to much more easily code or develop our machine learning, our probabilistic models, and then the time to develop and the complexity to develop these probabilistic models are going to be much reduced. And this is going to be quite nice and quite going to have big consequences, because the box loop, something that Celia just told you this morning, okay, it's going to be easily implementable in this context. So when we are doing probabilistic machine learning, we try to resemble this loop, which is very close to how the scientific method works, okay? So we will start with some question knowledge, and then based on that, we will make some assumptions that will be encoded in the form of a probabilistic models. Then we will take our evidence, our data, and then we will try to discover patterns. Once we have done that, okay, we are going to try to explore the insight that we get with our model, okay, we are also to make predictions, and then we are going to criticize the model, which is to falsify the hypothesis or falsify the assumptions or to verify the assumptions that we have made. And then after that, we will iterate again, okay? And the nice thing is like we are going to, using PPLs, using probabilistic programming language, we will be able to do that in a quick way, okay? I'm going to refer back to deep learning, okay? It's like when you are in Keras and then when people like start to adding layers, tuning the different architectures of the neural network, it's just simply changing line of code. One line of code, then you run again the algorithm, and then you see the performance, then you try something different, you run again the algorithm, then you see the performance. So the idea with PPLs is we will have the same. The question is like, now it's not going to be a problem of like changing the layer of the neural network. It's going to be like in the context of probabilistic AI, in the context of probabilistic models, like adding this random variable to represent this latent factor, modifying the prior of my model, doing all this kind of stuff, and then do this loop is going to be quite easy in the context of probabilistic programming languages. Yeah. So at the end, so these probabilistic programming languages, they are kind of bringing a kind of democratization again to this probabilistic AI. Yeah. So, but the reality is like PPLs, so probabilistic programming languages, they have been around for quite a few years. And at the beginning, what we call the first generation of PPLs, they were aiming to really, model every possible computable distribution. They try to be very general. And the kind of inference, which is the kind of learning algorithm that we employ in probabilistic AI, the kind of inference algorithm for this first generation of PPLs was based on Monte Carlo methods, okay? The problem was like they were very general, but the Monte Carlo methods were not very efficient in the context of large data samples and high dimensional models, okay? So this is because people developed a second generation of PPLs that has one of these like called InferNet by Microsoft Factory or also Mammoth. We were involved in the development of this PPL. And in that case, so the inference methods moved from Monte Carlo to variational message specific algorithms with the idea to scale to large high dimensional models. The probabilistic model that were able to be represented within these PPLs were restricted. And then, when people started to look more specifically into images, wanted to analyze text, different kind of data, these PPLs didn't apply quite well there. And then a new generation emerged recently, okay, of PPLs where we can find probabilistic programming languages like Pyro, the one that we are going to see here, Stan, probably Andrew will teach you something about this PPL on Thursday, but there are like other alternatives. And most of them, all of them, they rely on black box variational inference methods, the kind of inference method that we will see tomorrow, and also a new family of Monte Carlo methods, which are called Hamiltonian Monte Carlo. And the idea is like these models are able to scale to very large data samples or very high dimensional models. They are able to represent very general probabilistic models, even though they have a focus on having probabilistic models with deep neural networks, okay? Something that you will see, for example, specifically on Wednesday, okay? Perfect. And the idea is like, down there, they rely on deep learning frameworks, okay? So all these PPS, they rely on PyTorch, TensorFlow, they rely on deep learning frameworks with the idea of, being able to take over of utilize specialized hardware like GPUs in order to really accelerate computation, and also something that will make our life very easy, okay, in order to implement this inference algorithm, this black box variational inference, but also this Hamiltonian Monte Carlo is like having this idea, having this functionality of automatic differentiation, okay? But the question is like, among all these PPLs, this last generation of PPLs, these models, probabilistic programming languages, we are going to focus in Pyro. Mainly because it's a very nice probabilistic programming language developed by Uber, okay? There is a nice community of contributors around, so it's an active open source project that relies on PyTorch, okay? And you can have like nice things like GPU acceleration. But the question is like, it's one possibility, okay? And the main focus here is not going to be to specifically teach you Pyro, but specifically teach you the abstractions that are behind Pyro, because these are kind of abstractions are the same ones that are present in other PPL. So for you, it should be easy once you have learned one PPL to move to another, okay? So what? Any questions so far? Okay, nice.
So was the switch from the different generations, was it fueled by a can you go towards deep learning methods, or was that because of the limitations of the previous?
Exactly. I mean, it's like, at the end, it's like, yes, it's the limitation, in the sense like, these guys were very general, okay? And they work very well. But then big data came. And also like high dimensional models with a lot of parameters, like more complex models. And then they were not able to deal with them. It was like, I mean, like having new problems, okay? It was like the real need of changing, yeah. These were able to deal with all these very large data samples and very high dimensional models, like models involving like billions of random variables, okay? The problem is like suddenly people got interested like in image, in text, and then you need to model highly nonlinear conditional distribution or highly nonlinear relationships between your different random variables. It's like people need to use neural network within the probabilistic model. And then when neural networks, people realize that we need to go in that direction in order to make our probabilistic models better, then all these PPLs, they were not designed for that. Yeah. And this is because, yeah, we have a new generation. Yeah. Perfect. No.
Can you explain, so probably you were focused on Pyro for most of the time. Can you explain the difference between like Pyrostat and whatever and what that is?
I mean, let me see. So Pyro is, let me see. So let me see, like PyMCC, InferPy, and Pyro, they have a strong focus on having probabilistic models with neural networks. Okay? So Celia showed you this morning this kind of Bayesian network when you have a random variable that takes two values, yes, no, okay? Another two values, the earthquake, yes, no, okay? And then the relationship was a conditional probability table, okay, which is a very simple step function, okay? But with these PPLs, okay, you can model like very complex. You can take like an image can be a random variable, okay? Stan is more focused on classic Bayesian statistics, classic Bayesian data analysis, and the kind of inference engine it has is mostly Hamiltonian Monte Carlo, okay? These other guys, the main inference engine is black box variational inference, even though, for example, in Pyro, you can also exploit this Hamiltonian Monte Carlo. But these guys are really focused on having deep neural networks within your probabilistic model. Stan is kind of more general, PPL. Yeah. No more question? Okay, perfect. So another thing that we are going to do is like, yes, we are going to start to see how Pyro looks like. Perfect. So we have this GitHub repo here. Let me see, but you can just, if you go to the GitHub repo of the probabilistic AI, of the ProbAI, here you have the link that corresponds to, to this after lunch session. Yeah. If you click there, then you will arrive to our repo, the repo that is designed for today after lunch and tomorrow the whole day. Okay, here we have all the materials. And then, right here, okay, you have a link to the repo that we will use during the afternoon. Okay, the students one. Why the students one? Because we have exercises. Perfect. And then, by the end of the day, we will also release or tomorrow, we will release the same version of the notebook with the solutions to these exercises. Perfect, so you can just double check and so on. But right now, this link is not really working, and then you have to click here, and then you will move to the students' PPL's intro notebook, okay? And then, I don't know, just in case some of you are not really familiar of how Google Colab work, I don't know, has any of you been working with Google, or has not been working with Google Colab before? Okay, apparently like some students, I mean, perfect. So I will give you just a very quick intro to Google Colab, just in case, okay? So the main thing that you have to take into account is like when you open Google Colab, you need a Gmail account. Perfect, okay? Google Colab is a Jupyter notebook that runs on the cloud, Google Cloud, okay? And the nice thing, and this is probably one of the most nice things, is like, you know, you can just change, perfect? If you want to run your notebook on a standard CPU, or if you want to run your notebook in a, for example, a GPU or something which is called also TPUs, okay? You can just change that, even though we don't need that today, okay? Tomorrow, yes, but just to let you know, okay? Perfect. So you have the basic functionalities of a Jupyter notebook here, and probably the most interesting thing for you guys that you should not forget is like, please, I mean, it's like when you make the link, as it says here, you cannot save the changes, okay? So what you have to do is like, you have to click here and save a copy of the notebook in your Google Drive. Perfect? So it's like when you work today, this afternoon, every change that you make will be saved. And you know, if later you want to have a look at this notebook or whatever, and the kind of stuff that you wrote, so you will be able to recover it. Otherwise, if you don't save it in your Google Drive, you can work with the notebook, but the changes that you introduce, they will be lost. So it's up to you. Perfect? So maybe it's a good idea that you make a copy to the Google Drive. And well, Shift Enter for running the cell, okay? Or maybe you just click here on the play button that appears here. It's also another alternative. And then you can just sequentially run the cells. It's just a standard Jupyter notebook. Yeah. I'm assuming that you're familiar with Jupyter notebooks, okay? Yeah. So any question in relation to this? Yeah. So I think like Thomas, well, I mean, just maybe to mention like, you know, during the exercises is also a good idea, like you can just plug the laptop of one of you, okay, and see it in the screen, but we will come back to that later, yeah. So now Thomas is going to, yeah, to continue this one.
Okay. Thank you. Okay, so the rest of our session here is going to be devoted to the Jupyter notebooks that Andrés just introduced, where we are going to introduce some of the main high-level constructs that you'll find in Pyro, mainly focusing on modeling using Pyro. So there's sort of a lot of stuff that we are going to hide behind the scene that concerns parameter learning and inference, so all the nice stuff that Celia presented earlier today, but this is something that we are going to dive into tomorrow. So for today, it's selected aspect about Pyro for doing the modeling part. And here I should also really emphasize the selected part, because there are many other aspects about Pyro that we are not going to cover here. So it will be more these main constructs that you can use for doing model specification. And which you can also take on if you want to play around with other probabilistic programming languages. So, Andrés already introduced the notebook here, and what we are going to do now, we are going to have a very brief session here before we have a small exercise combined with a small break. But we are just going to introduce a few basic building blocks, and then you can play around with that and just get a feel for it and see that everything works on your side. So we are going to rely, as said, on Pyro, imported up here. And Pyro provides, since we are focusing on probabilistic models, we are going to look at different types of probability distributions. And here Pyro has a rather large family of distributions that you can use for your model specification. So Celia already listed some of them earlier this morning here when she had specified the list of conjugate distributions. This is not something that we'll be concerned with here, but just to let you know that there are these links. So for defining different distributions, we use the distribution library up here from Pyro, and we can then define, for instance, a normal distribution, dis.normal, and here we define one with a mean of 0 and a standard deviation of 1. And if we run that piece of code, then we get an object here corresponding to our now defined normal distribution. So once we have our distributions, we can also sample from them. So here we create a sample from our object, normal.sample, and we output the value. And here we can see that the value that we are outputting is then embedded within a so-called tensor, which is a concept from PyTorch on which Pyro is built upon. If you run this code another time, so now we got -1.1, we'll sample a new value here. So each time you run this piece of code, you'll sample a new value. And these values, as again, they're embedded within PyTorch or Pyro tensors, and Pyro, or these types of tensors, can in generally be considered multidimensional arrays. So if you want, now we got one scalar output. If you want to have a tensor of 3 dimensions, let's say you have 3, 4, and 5, then you run a sample like this, and then we have our values that we sample outputted in a tensor of this specified shape here that we have specified up here along these 3 dimensions, with length 3, 4, and 5. You can also, if you have a sample or a tensor, you can also query the shape of that, which is very convenient when you start to do also your debugging of your models. So here you, for instance, we sample from our tensor up here, and then afterwards we call sample.shape, and then we get the shape of the sample, the shape of the tensor that we have just created. We also have various operations that we can do on the samples, the tensors that we've generated. You might want to calculate the log likelihood or the log probability of your sample based on this particular distribution that we're working with. So we have a normal distribution, so we can invoke normal log.prob on our sample, and then we get a log probability for each value in our tensor object. And if we then want to calculate what is then the log probability of the entire sample, we would then sum it up. And here we use torch.sum because everything here is placed within a tensor object. And then we get a value here, minus 79 point something. When defining your distributions, you can also embed different distributions within the same objects. So here we are, for instance, defining 3 normal distributions with different means, 1, 2, and 3, but with the same standard deviation. So here we define our normal distribution, and when I then sample from that, we get 3 values out. So embedded within one tensor, we get 1 value for each of our different normal distributions that we've defined, and we can obviously do that again, and then we get new values. And for here, we would be able to also to calculate our log probabilities, and this is what we get. We get 1 log probability for each value that we've generated from each sample from our object. So that was sort of a very brief introduction to some very, very basic concepts from the Pyro language. And what you should do now, what we will try to do now, is just for you to just get Pyro started in Google Colab, play around with the first part here on top of the exercise and see that things are working on your side. If you have any questions, we come around to take them there. And then we'll also combine it with a break. And how much time should we say? 15 minutes? So let's start again a couple of minutes after 2. And maybe as Andrés pointed out just before he handed over the microphone, it might be nice for you to use the screens connected with the tables so that there's a better opportunity for collaborating on solving these, although not difficult exercises, but then again checking out that the equipment also works there. So, let's work with this until a couple of minutes past 2. So how do you... Okay, let's. It's time to get. It's time to get started again. It's time to get started again. I hope that you all had a chance to fill up the coffee mugs. So it's time to get started. Good. One question we got during the exercises here is concerning if you try to download the notebooks and run it locally. If you do that, then you also need to have GraphWiz installed in order to have things up and running. So that's just a minor thing, but otherwise everything should work out of the box. But GraphWiz needs to be installed locally if you want to do it like that. Good. So what we'll be looking at now is to start to investigate the notion of models in Pyro. So now we are really taking the step into building our own probabilistic graphical models. And we are going to use a very, very simple model as a starting point, and then we are going to elaborate on that and extend that throughout this session here. And then you are going to make further extensions to that a bit later during upcoming exercise sessions. So in Pyro, a model is basically defined as a stochastic function, meaning that every time that you run the model, it returns a new output. And the basic building block is the primitive stochastic function offered by Pyro in the form of a Pyro sample statement. And this is sort of a Pyro sample statement is basically Pyro's way of defining stochastic variables or random variables, just as Celia introduced earlier today. So our very simple example here, we are going to model the temperature. So we are going to work with temperature measurements, and as a starting point, we want to define what is sort of a random variable capturing the temperature. And for that, we build a Pyro model, and this is by defining a function called model. And here, within the model, we have our random variable, which is called temp. And this random variable is defined through the Pyro sample statement that is also given the variable the name temp. So we have sort of a name overlap here. And afterwards, we are also saying that this random variable has or follows a normal distribution with a mean of 15 and a standard deviation of 2. So thinking about temperature in Trondheim around this time of year. So, and then afterwards, we return the value provided by our sample statement. And if we run the model twice, so what I've done below, then you see that you get two values, two scalars returned, each embedded within a tensor object. And we just call the model twice, and we have this random stochastic behavior in the sense that we get two different values returned. Pyro also has some neat functionality for rendering your model, and that is something that's quite useful also when you start to extend on these models here. So if you call Pyro render model, then in this case here we get something like this. We have our random variable temp, and we've specified also here that the distribution should also be returned, and here we can see that temp follows a normal distribution. Now, one thing is to know what the exact temperature is, or modeling the exact temperature, but we usually use sensors, measurement devices, to measure the temperature. And these sensors or measurement devices are typically noisy, so they provide a noisy image of what reality really looks like. And this is what we are going to try to extend our model with. So we define a new model here that is basically a composite of now two primitive stochastic functions that would be two random variables. And the first part of that we have here is the same as we had before. So we have a temperature variable called temp with a normal distribution with mean 15 and standard deviation 2. And then below we define a sensor variable that has a conditional normal distribution, conditional in the sense that the mean of the normal distribution here is just the value that we have just, or the value of the variable that we've just created, and now with a standard deviation of 1. So this standard deviation of 1 is an expression of how accurate that we believe our sensor actually is. So the more accurate sensor, the less standard deviation that we have here. And now our function returns two values, a tuple with two values, the temperature value and the sensor value that we have just sampled. And we can see again what the model looks like from a nice interpretable graphical perspective, that we have the temperature variable and the sensor, and both of them follow a normal distribution. The latter condition on the former. And we can sample from our model, and this is just the same that we did before with our very simple model, and now we get two values returned, one from each of the two variables included in the model, and which we return with a return statement on both. Okay. Are there any questions so far about this type of model construction that we see here? Okay. Yes?
If I multiply temperature by 0 in the argument, it's still going to be considered as like dependent, right?
Yes, so maybe I should have clarified that, but then you gave me a nice opportunity. So here we have a very, very simple model class with a simple linear dependency between the two variables that you defined. But this here being a probabilistic programming language, you can in principle consider, or you can embed whatever kind of code that you would like in your model specification. So if you want to extend it with for loops, you can do that. We'll actually see that later on, and you will also be working with that. And you can use whatever kind of transformation of these values that you would like. So you could build up complex nonlinear relationships between the variables for capturing whatever kind of model that you're interested in. Yeah?
I think it's maybe a question about semantics, I guess. So when we're talking about models, this is not something that we learn, it's just some process that's happening that we are observing.
Yes, so maybe one point. So I don't know whether you could hear the question in the back, but if you couldn't, then for questions, I think you can actually, there's a mic on the table that you can press, and then you can get on the loudspeaker and then say. Sorry?
Where do we have to speak?
I don't know how sensitive it is. But in any case, so the semantics here, this here is just a question of whether this is something that we built or whether it's something that's going to be learned. So for now, we are only trying to do handcrafted model construction. So in particular, the model structure in itself, the relationship between the temperature and the sensor variable, is something that we assume is fixed a priori. Later we'll see how the parameters, we can start to learn them and reason about them, but generally we'll see consider the model structure to be fixed. So the conditional independencies that you have in the model are assumed to be known. Okay, did that... you don't have to press that. Thank you. Other questions? Okay. So maybe also adding to that, what we now see here with our more complicated model is that we have now a model that defines a joint distribution. So that would also be the semantics of these models here. Again, pointing back to Celia, that we have a probabilistic model that defines a joint distribution as the product of the individual distributions that is encoded in the model. Good. Now, once you have your model, you would typically be interested in curing it trying to investigate it further, inserting evidence in some nodes, trying to make inferences about other nodes or variables. You might also want to do learning of parameters, both from a maximum likelihood perspective and a Bayesian perspective. And for that, we are using the inference functionality provided by Pyro. And here I have sort of deliberately hidden some code in this part of the presentation here. We still need to run it. So what I'm doing here is to define a function called SVI for stochastic variational inference. But we are not really going to delve into what kind of functionality is within this function. You can just expand on this here. And then you can see for yourself and try to deduce it. But this is really one of the topics for tomorrow's session. So I'm not going to say anything more about that, except that we are using that below to make inference in our models that we are going to define to basically query that. So it's an auxiliary function that we will be using for now. Now for this paves the way for doing inference in Pyro, inference in the model that we define. And as a starting point here, we can start by conditioning just on a single observation that we have. So we make an observation about a sensor value, and now we want to query what is then our probability distribution over our temperature variable. And we do that using the Pyro observed construct that we have. That we have down here. So up here, we have a Python dictionary where we are defining the data that we have available. So it's just a dictionary where we have our sensor. I define have the key sensor, and then I have a PyTorch tensor where that includes the value 18, meaning that I make a sensor measurement of the value 18. Now I want to do inference in my model by conditioning on this observed sensor. So I provide that observation here as an argument for the model specification. And then I extend the sample specification of the sensor down here, where I provide ops equals ops.sensor or ops sensor, which is basically just providing this value 18 here to my observation. That means that I have an unobserved, a hidden random variable temp, and an observed variable sensor in this case here. And if I plot that or run it, then I get a model like this. So we can also see we are using sort of basically the same graphical semantics as Celia did. We have the gray nodes here that represents that the variables are observed, and the white nodes up here meaning that they are unobserved. And that's sort of based on this use of the keyword observation up here. We can now query our model, so we do inference, and here it's just an application of Bayes' rule. So we calculate the probability of temp given the sensor values equal to 18, and here we have Bayes' rule. And for doing the actual calculation, we are relying on the function that I just flashed before your eyes before, SVI, where it has 3 arguments here: the model, the observations that I would like to provide for my model, so the evidence, and then I'm also asking to have some plotting done. And if I run this, now it takes a bit of time. So here there are already some details revealed about how we are doing inference. So we are optimizing or maximizing a so-called evidence lower bound function, elbow. And this elbow function, the output of that is returned here. And what we see down here is just an illustration of these values that we are calculating, the elbow values, and we are trying to maximize, and this is sort of what is illustrated here. But all these details will come later tomorrow. Then when running the model here, then in the latter part, I am also querying parts of Pyro that includes information about the posterior distribution that I've just calculated. This information is hidden away in some internal pyro parameters that are accessible from this pyro param construct here. Now I know the name of the variable that I'm interested in. It has a normal distribution with a particular mean value and a particular standard deviation. And this I can extract and provide out here. So this here is my posterior distribution. I started with a mean of 15. Now I started with a mean of 15. Here I have a mean of 18. So that may not be quite obvious why it's higher, but this is simply because we have sort of a stochastic, noisy approximation procedure here. And then we have a standard deviation over here. Good. But these details will become apparent, will be detailed much more tomorrow. Now, once you have, now we know how to do inference. And as Silje pointed out, we can also do learning. And as a starting point, we can do investigate the possibility of doing maximum likelihood. Sorry, I'm maybe getting ahead of myself. So we've done observations of one variable. We can also have observations of multiple variables and have multiple instances or model specifications provided. So here in the next part, we are defining a set of random variables based on a set of observations, and we are providing one temperature variable and one sensor variable for each observation that we made. So you should think about this as you are making observations, multiple observations, maybe over time, maybe at different locations. So here I think we are writing up this, that we are doing this here. We are making multiple observations over time. But assume independent of each other. So we have a bunch of observations up here that we made 18, 18.7, 19.2. So these are observations from our sensor. And then we construct a model with two variables for each of these observations, one for the sensor variable, one for the temperature variable that we're interested in. And if we render this, we get something like this. So here, going back to the question before, what happened if we had what can we actually do within this, what kind of code can we have within our model specifications? So this here is an illustration where we also embed for loops within our model specifications. So I'm here looping over the sensors that are embedded within the PyTorch dictionary object over here, and creating a temperature variable and a sensor variable for each element that we have for sensor up here in our sensor object. And each of these variables here are then given a particular value indexed by I. So this is the I that we are running our for loop over. And here we are just rendering the result of that. So it's not a very interesting model. It's basically just 10 different model fragments that are independent of each other that we can reason about. And we can also do inference in this model. And now we are providing evidence on each of the sensor values. So we will therefore also get a value, a posterior distribution for each of our unobserved latent temperature variables that we have on top. And the outcome of our inference algorithm is given below here, where for each variable, it simply returns the so-called location and the scale of that variable, and it runs through indexed out here by 0, 1, 2, down to 9, corresponding for each of the variables that we've just created. Okay. So this is sort of the way that we do inference in Pyro, using the observe keyword for the sample statements. Next, we are going to continue with the part that I was too eager to get started on learnings. But before that, are there any questions about the inference setup that we have here and the way that we do inference? Yeah?
Would it also work if we just have deterministic function? In what sense do you mean that we just have deterministic functions within the model specification?
Yes, in the sense that pyro.sample is the way that we define random variables in Pyro. So in order to insert evidence or query a variable, you need the sample statement. So this is really the most primitive functionality on which you construct more complex models within Pyro.
But you can also like have normal distribution with zero variance, right?
Yes, so I that would sort of be rather degenerate in that case. I would expect that there would be some kind of exception that would be thrown here. But there are ways to specify deterministic functions within Pyro. So they have a particular deterministic class. What kind of constraints it may have, I can't recall.
Because it's like would be a tool for inverting non-invertible functions, like the functions with many arguments.
Yes, but
if I know the result of function with many arguments, what is the like posterior distribution? Yeah, but it's just like
I'm not quite sure whether we. Let's take that in the break. So it was a question about deterministic relationships within PyTorch or within Pyro, what you could include in the model specification here. And there are ways of including deterministic functional relationship between the variables. Okay. Yeah?
And instead of setting the last one up with the for loop, can you do it also in the vectorized way?
One more time, please.
Instead of setting the last model that we saw up with the for loop, can you also do it in a vectorized way?
Yes, and we are going to return to that a bit later, just before the break, and then we'll see how that can actually be done. But it's a very good point because it's not very efficient this way here. Yeah?
Technical thing. The moment the ops goes into the model doesn't have an explicit return statement anymore. Is that something that's taken care of in the SVI function, or how does that?
Yes, so when you do the inference part, and we're going to see that tomorrow, so very briefly, and then we can take the details during the the exercise. But the way that you construct your inference functionality, there you specify so-called guides that need to match up in terms of variable names with what you have in your model specification. So that's how you handle that part. But we'll see that much more in detail tomorrow. Okay. So let's continue here. So now we specified a mean temperature as our prior distribution. We had a prior of 15 and a scale of 2. That was sort of the way that we specified our prior for the temperature variable. Now, what if you don't know that? Then you could start to try to learn that, and as Celia explained, one way of doing that is to refine a maximum likelihood estimate for that parameter value. And graphically, the model that we want to specify looks something like this. So we have our temperature variables here, the sensor variables down here, and then the temperature variables up here. Their distributions are parameterized by mu, corresponding to the mean value that we may not know about. So for handling that, or for modeling that we want to learn this, we are going to use a statement in Pyro called pyro.param, so for parameter. So we are specifying the model. So again, up here, our observations. Then we introduce a parameter called mean temp with the corresponding defined name here, mean temp. They need not be the same, but we do that for readability. And we initialize it to a given value, let's say in this case here, 15. And then we have our for loop from before. We are iterating over the sensor values, and we have a temperature variable here with a normal distribution that is now parameterized by mean temp and still given the standard deviation of 2, just as we had before. And then we have our sensor variable here, also specified just as we had in the previous example. But the main difference here now is that we say that we don't know the mean temperature, the parameter mean temp. We assume that it's something that we want, or we define it as something that we want to learn, and we do that by embedding that within the pyro.param statement that we have here. And if we learn that, and visualize it, we get a model structure that looks like this, so expanded from the illustration from before. And now we can do learning again, so it's just the SVI function being called. And now we are running. And while it's running here, so what we again see, we have a maximization of the elbow, and at the end we return, pick out the mean temperature from Pyro parameter, so-called parameter store in Pyro. We save that and print out the value, and that's 19.56 that we've estimated the mean temperature to be, the mean temperature parameter. We can also describe this here as our learning problem here within a Bayesian setting, where we are now putting up a prior distribution over our mean value. So before we took a maximum likelihood perspective. Now we are positioning this, we are moving to a Bayesian learning setting, where we are saying that this is an unknown quantity that we have prior knowledge about, so we give it a prior distribution. And when we can define this model here, let's just render it from the beginning. So now, where we before specified mean temperature using a Pyro parameter construct, saying that it's a parameter, now we simply define it as a random variable, as you do when you're considering it in a Bayesian setting, with a prior distribution 15 that is normal distributed, with 15 and 2 for the mean and standard deviation, and then we are looping over our observations here. We can render our model, and we can see that we have a model structure looking like this. Yes?
Sorry, probably a stupid question. Why do we do maximum likelihood on top of the variational approximation?
So
variational approximation just fits some variational distribution for everything which is not evidence, right?
yes. So
it also fits all the parameters on the way, right?
yes. So the question here was why we are looking at this as a maximum likelihood estimation when we're also doing variational inference. So this is partly just the way that I specified my model. I did not wish or was not able to provide a prior distribution for the mean temperature, but I still want to do inference. I still want to do the learning part here. So I'm casting it as an optimization problem where I'm trying to maximize a particular lower bound that we'll see tomorrow, and part of that is also optimizing or maximizing with respect to this unknown parameter. But that's sort of embedded within the overall learning setup. And when we move to our Bayesian learning scheme with variational inference, or a Bayesian learning scheme where we're treating the mean temperature here as a random variable, we now perform inference in the sense that we are calculating the posterior distribution over the mean temperature here, conditioned on the observations that we made. And we do that here. So I'm also timing how long time it's going to take. And after model learning or model inference, we are returning what is the probability for the mean temperature given our observations. And now we see that rather than having a point estimate, we get a distribution. So we have a normal distribution with a particular mean and standard deviation. And we can also visualize that and see sort of the difference between these two different approaches. So for the orange line, this is my point estimate by the maximum likelihood approach. And the blue curve, that's the one that I returned when I took my Bayesian approach for doing learning, which boiled down to doing inference in our model. Yes, so here we are really interested in trying to quantify the uncertainty that we may have about our model. So the last part before the exercise and the break relates to the question that we had before, whether one could also vectorize the model construction and the inference. And we have functionality for doing that. So if you, for instance, investigate the model that we have here, and in particular we look at the d-separation properties that Celia introduced for analyzing this model, we can see that we have a diverging connection on top. And if you condition on mu up here, you actually have that these underlying model fragments become conditionally independent of each other, meaning that you can do inference in each of these fragments here independently, and thereby also speed up the inference. So if we see before we I took the timed it, so we spent 10 seconds before. But if we specify this independencies that we have in our model using Pyro's plate construct, meaning that rather than having a for loop here, we are using Pyro plate, which tells Pyro that these elements, model elements, fragments that we have underneath are in fact conditionally independent of each other, then we have a ways of speeding up the process or speeding up the learning. And we can also have a graphical illustration of that fact. So here we again, when we render it, we see that we have the temperature and the sensor variable embedded within a plate construct that would be replicated 10 times if we unfolded it. And now if we do inference, we see that things run much faster, so we have reduced by a factor of 4 from 10 seconds to around 2.5 seconds. So there's really a lot of speed up if you explicitly tell Pyro about these conditional independencies. Yes?
Is there any reason why Pyro couldn't figure this out itself? The model looks the same if you know, like.
So it's the way that the underlying computational graphs is being analyzed. So this here is one way for the model to specify what are the conditional independencies that you have in your model. It could also be that you may know about independencies that could be included within the... I was just thinking about whether one could also imagine numerical examples where it would be difficult for Pyro to figure that out itself, but I would not be able to come with that on the fly. But this is sort of the way that you would explicitly tell Pyro about these independencies. I don't know whether you have anything that you want to add. I think we are a bit behind. Okay. Other questions? Yeah?
Technical question about scale. Would that scale up enough to be able to run this on the GPU capabilities of the PyTorch, which is probably underlying error?
So about how this scales up so that you can run it?
So if I increase the size of the problem and it still remains theoretically parallelizable, would that also be able to make use of the GPU capabilities that are baked into the framework?
Yes, so all the functionality here in terms of inference and learning relies on PyTorch and PyTorch automatic differentiation capabilities. So in that way, to the extent that you see that PyTorch will also scale up, you would have the same type of scalability that you have here. There could be aspects of the models that makes things more difficult, but in general, Pyro are relying on the underlying inference capabilities or automatic differentiation capabilities of PyTorch. Okay. Yep.
For this example, it's like 10 sensors, and does it make much difference if we just use multi-dimensional distributions, like for example, 10-dimensional?
Yes, so you could, in principle, embed this and tell Pyro, and this is not something that we have really covered here, but you could specify your model and then push the samples that you generate into a multidimensional distribution, so you're pushing them into so-called events, and then doing your calculations there. But then the problem with that approach would be that you have a model where you have some obvious conditional independencies, but by simply pushing everything into one object, you would not be able to exploit these dependencies during inference. Whether you would actually be allowed to do this here with plates, so starting with defining a multidimensional distribution and then afterwards using plate, I'm actually not quite sure what the result would be. But if you're adventurous, then it might be something to explore in the exercises. Other questions?
Yep.
Okay,
There's
in
like, sorry, no, there is a question here.
Sorry.
Is there a reason why Pyro doesn't do it implicitly? Like, is there a special functionality that it has to address? Because since, if the functionality is explicit and it's faster, why not make it like an implicit way how Pyro kind of identifies the plate structure?
Well, I guess it's because then you are basically you're giving all the Python functionality when you're specifying your model construct. So that would basically be same as saying that you rely on Pyro to be able to disentangle your code and identify from your code what would be independent and what would not. And this way here you have sort of a way of explicitly specifying what are sort of local variables that belong together within the plate and what are global variables and how are they linked together what's dependent or conditionally dependent on others. So with this degree of freedom here, there would also be a price to pay, and this is one of it. Yeah? Yes. So, this is basically an underlying aspect of the inference scheme that we employ, that you need to specify the distribution family of your posterior distributions. And you can do that explicitly or implicitly using Pyro. Actually, here we've done it implicitly, that it would be normal distributions, and then this is what this is sort of the default that is being used by Pyro. But you could also pick out other distributions, and we're going to see that tomorrow, how that can be done. So I'm sorry for pushing a lot of things for tomorrow, but that's something to look forward to that. Yeah?
The general question of interest, is this something that you yourself use a lot in research?
Yes, Pyro is my go-to language when doing modeling.
And what do you research?
Sorry?
What do you research?
I have a background in probabilistic graphical models. So this is sort of the area that I'm sort of moving around in.
Yeah, but I mean, we have also to consider that there is like sometimes, so you have a fixed model, okay, which is completely fixed. Okay, it may happen like maybe payoff to do like all these algorithms ad hoc for this specific model. You don't have to go to Pyro, okay, because there is always an overhead, okay? So like going to Pyro is like you don't have a clear idea with the specific probabilistic model you want to use, and then you want to explore a wide range of probabilistic models. Then moving from one to another means really, if you don't use Pyro, it can mean like a lot of work, okay? Yeah. So like unless you have like a very clear idea, like for example, variation autoencoder, something that we will see also tomorrow, usually people can be used safely without Pyro because it, you will stay there and you don't have to move around. Yeah.
I was thinking about, PyTorch has recently done this distributions module.
Exactly. Well, actually, all this stuff comes from really the distribution part. The distributions themselves come from PyTorch.
Yeah.
Okay, Pyro gives you on top the inference engine. Okay, which is like the variational inference engine or the Hamiltonian Monte Carlo inference engine. This is what Pyro adds on top. Plus the ease of moving around, like for example, using this plateau construct. So all this kind of a different level of abstractions. Yeah.
Yeah. But again, as Andrés also mentioned in the beginning, there are many different languages that you can explore. And if you know that you have a particular model class, let's say Bayesian networks where everything is discrete, then this would probably not be the way to go. Then there are other tools that are much more efficient that target these models here in particular. So this is also to really have the flexibility that we're looking at this. Yeah? This is also part of Pyro, yes. So the question was whether there was also support for MCMC, and this is also the case. Okay, I think, do you know on the timing? Okay. So in that case, then maybe we can move on to the first exercise that we planned. And this is mostly for you to go through the code that we've just presented here, play around with it, and in particular try to explore what is the meaning of specifying prior distributions. So by experience, coming up with sort of what is a suitable prior, how does it actually balances the amount of data that I have. These can be sort of difficult concepts to get a hands-on feeling of. And this is sort of one of the things when you go through the notebooks and play around, then try to also play around with the way that you specify prior distributions. You can also change the priors from normal distributions to something else. Maybe consult a bit in the Pyro documentation to see what kind of distributions are available. But getting a bit of hands-on feeling there would also be sort of quite nice. And I think we set aside, was it 20 minutes?
Well, like in reality, it's like 10 minutes for the exercise plus another 10 minutes for the break. So, like in total, we will be back here in 20 minutes, like 5 minutes past 3. So, yes. You can just go for the coffee right now, or you can just wait. It's like we have like 20 minutes. Okay, perfect. Yeah.
Okay.
So so just one thing, like apparently the coffee is not yet ready, so maybe you wait a bit later. Yeah. Yes. Anyway, so, just remind you guys, like, so there are like a bunch of TAs around. Thomas and I will be around. Just feel free to raise your hand so we can just address specific questions that you have, okay? So it's part of the learning experience, okay? So please ask, okay? Yeah. Yeah, perfect.
That's a good point.
Yeah.
Maybe one could also say that one should be a bit...
Yeah, I think I can, yeah. Yeah, let me see. Yeah. Yeah.
So let's just see. I think it's much more stable now, also when you have 100. So let's see, if we have this as a starting point, I can also just...
No, it's okay. Let me see. Yeah, it's okay. Yeah.
So keep it like that, and then we move to 100, and then you can see.
Exactly. Yeah.
And also that.
Yeah. Okay.
Also say.
Okay, guys. Okay, so we are going to continue, okay? So I'm going to spend just a few minutes, okay, discussing a bit about, like, which was the purpose of this exercise, okay? And, that start to get a bit of feeling, what do we really mean by probabilistic model and capturing uncertainty? Just to recap, we are supposed to be working on a problem where, we have a temperature sensor, okay? We take sensor measurements that try to capture some real thing, which is the temperature of the room, which cannot be observed. We can only observe the temperature of the room through the sensor, okay? And then Thomas, so you have to build a probabilistic model. Perfect. On top of that, capturing these noisy sensor measurements, how we cap different measurements across the time. And the problem was to capture, like, the mean temperature. Perfect? Yeah. So let me see. So I just took here, like, 10 measurements. So I'm just assuming I have 10 measurements, okay? So now I'm going to run inference, okay, and then this is the posterior distribution over the mean temperature, the value I want to learn about using this measurement, okay? So this posterior is a normal distribution, but it's a normal distribution which is like half this shape, Perfect? So it's a density. It's telling you, like, the real mean temperature is somewhere else in this range with high probability. Perfect? So if I just focus on the measurements itself, okay, on the measurement itself, and I take the mean of these measurements, this is where the mean is placed, okay, the empirical mean, which could be kind of point estimate. But the posterior is telling me that the real temperature lies in this range. And here we are combining two things. We are combining the data, the observations, okay, but we are also combining the prior knowledge. Remember, here we were able to provide prior knowledge. So, like, a priori, we think that the temperature of the room is 15 degrees. Perfect? So combining my prior knowledge with the measurements, I get back to this estimation. And as you can see, I'm not providing you like a value. I'm providing you a density, a distribution over the possible values. I'm capturing uncertainty. Okay? So let's assume now that I observe 100. Okay? So do you think like with 100 observations you will be more sure about which is the real temperature of the room? We should, no? And this is what is reflected, okay, in the result of the inference. Now, yeah, the uncertainty that I have, the range of the real temperature is smaller. Okay? And this is what I can observe here. Perfect? This is the nice thing. And then I'm combining expert knowledge, I'm combining my prior with my data. So imagine that I assume that my data, but my prior, I'm not really sure. Okay? How can I reflect that? By having a prior, more flattened prior. Okay? So if I'm less convinced, if I have less knowledge about where is the true temperature of the room, now what is going to happen is like the posterior is going to be centered around the data. So the data is going to have more weight. Okay? So before, when I thought that the average temperature of the room was 15 degrees, this blue density was moved a bit to the left, capturing that, it's a mixture between the observation, 18, and my prior knowledge, 15. Now I have softened my prior knowledge. Now my inference has focused on the observation. Okay? But the nice thing is like we are also taking into account how precise is our sensor. Okay? Imagine that your sensor now is less precise. Okay? It's lower quality sensor. And then we can reflect that by having the sensor measurements, okay, has now a higher variance. What do you think? So if we have a less quality sensor, should we have the same certainty or the same uncertainty, or the uncertainty should increase or the uncertainty should decrease? What do you think? If you have a sensor with a worse quality, should increase. We should be less sure about which is the temperature of the room. And if we run it, this is what we see. What do you think is happening? The prior. Your data provide less information. Because your data provides less information, you go back to your prior. But if suddenly I increase the data, okay, I don't know, have to be careful with the inference. But if I increase the data, we move a bit to the right, okay? If I keep increasing, so we always have this kind of trade-off, okay? And the nice thing with probabilistic models is like we can explicitly encode this knowledge. We can explicitly say, this is my prior knowledge. We can explicitly say, this is the precision, the quality of the sensor, okay? And all this information is combined, okay? And then what you get back is this kind of estimation, okay? Perfect? So, questions?
Why is the variance not bigger if your data and your point, if your the data is saying that it's more on that side. Why is that? Because the variance not increasing with this big amount of data and this small amount? Is it because it's not modeled?
Let me see. So I'm going to reduce the effect of the prior. Okay, perfect. Yes, a bit. So the question is like, I have like 300 observations. When I increase the number of observations, the variance decreases. Okay, because I have more evidence, so I have less uncertainty. Okay, if I reduce the number of observations, the variance increases. Okay? If I increase the quality of my sensor, okay? So the sensor provides very precise measurements about the temperature, okay? And I can reflect that. Now I trust more my data. So my inferences are closer to this point. Yeah. So we have to move, guys. Okay? Perfect. So, I mean, let me see. So we are going to speak a lot about like priors, posteriors, likelihood in the coming days. So this is just to get you a kind of sense of what's going on here. Perfect? Yeah. So we are going to move and we are going to work in a different problem, okay? Again, we are going to be like a toy example, and this toy example is like, have two aims. So the first aim is like to get you more familiar with Pyro, and also the second aim is like to kind of build intuition about what does it mean to have a kind of probabilistic mindset when solving these kind of problems, okay? So we are going to assume this is a kind of, toy example, that we have an ice cream shop. Okay, and I'm the manager of the ice cream shop, and then I've been in this summer school, and then I come back to my ice cream shop, and then I say, okay, I'm going to try to apply what I've learned here, and I'm going to, I would like to have a good, I have like a good idea of how many ice creams I sell every day in order to have a good stock. Okay, and because my expertise tells me that the temperature, okay, that there is during the day, is going to affect the number of ice creams I sell, okay? So everybody understand, like, when there is like very warm, very high temperature, people like to go there and buy an ice cream. Okay, and then what I'm going to do is like, the guy at the ice cream shop, so he has just a temperature sensor. He's like measuring the temperature. Okay, remember, measuring this temperature, which is a noisy observation of the real temperature, and also accounting to the number of ice creams I sell, okay, during different parts of the day, and also I measure the temperature, okay? Then I'm going to record this information. Perfect. So let me see. I'm going to start here. These are the sensor temperature, the sensor measurements, all these values, okay? And these are the number of ice creams I sell. Okay, let's assume like every hour. Perfect? So this is the temperature in this time, in this hour of the day, and this is the number of ice creams I sell in this time of the day. Same here, same here, same here, same here. Perfect? Yeah. So I keep this, okay? And now I want to really have an idea, okay, and which is the relationship between the temperature and the number of ice creams I sell, okay? And then for doing that, I develop this probabilistic model that appears up here, okay? It seems to be quite complex, but we are going to go step by step, okay, and we'll try to understand it. Remember, so when we are doing probabilistic modeling, everything boils down to defining random variables, okay? So the first thing I'm going to do is like, I'm going to define a random variable, which is going to be this guy here, okay, which is going to model the sensor measurements of my temperature. Perfect? This is going to be a random variable. And this random variable is going to be distributed as a normal distribution. Okay? I'm going also to go down here a bit. Okay? The sensor measurement is going to be a random variable. And because it's a random variable, I'm going to use a pyro.sample construct to define it as a random variable. Perfect? And because it's a random variable, I have to define a density distribution for this random variable. And because it's a continuous random variable, taking continuous values is kind of standard to use a normal distribution. Perfect. So it's going to be a random quantity around a given value. Which value? The real temperature that is right down in this moment in time, okay? Which we don't know. Perfect? But because we don't know, this is not a problem in probabilistic modeling, because we can define the temperature, as we have done before, as another random variable. Perfect? Who is distributed as a normal distribution. Perfect? This normal distribution, again, reflects the random the randomness in the temperature of the day across the different times, okay? So it's not the same the temperature that appears in the morning that appears in the afternoon. There is randomness. And this randomness is, around a given value. Which value it is? The mean temperature of the day, which, because I don't know, I define it as another random variable with another distribution, a normal distribution. And now I provide my expert knowledge. Then I say that, like here in Norway, this time of the year, not this year, but 15 degrees. Okay? Perfect. Okay, now we have the temperature, like we did before, and now we are going to use, yes?
I cannot see that.
Oh, sorry. Yeah? Oh my God, let me see. Now.
The standard deviation of the sampling temperature somehow defines.
Exactly. This standard deviation?
Like the one, yes,
yeah.
This one defines like the variance of the temperature along the day.
Exactly.
Why do we need like a standard deviation for the mean of the temperature?
Exactly. The standard deviation for the mean of the temperature is going to be the operator. So I think that like the mean temperature across the days in Denmark, okay, are around 15 degrees, okay? But how much above of how much below 15 degrees? This is reflected by this value. If you expect like here can go like 5.25, then
is that like along the days?
Across the different days, yes. That would be like across the different days, okay? Yeah, that could be a way to fix it, okay? Another way to fix it could be like, and this is like we are kind of getting more Bayesian, but you can even like put here a very large number, okay, reflecting that you don't really know, okay? And then you just let the data tell you, okay? That could be another way, but let's think for the simplicity right now, this moment on time, that kind of reflects your knowledge, okay? Perfect, your intuition, okay? Yeah?
If your objective is just to measure this variability that you could have,
yeah.
So on the sensor variable, you go to define it as the temp and then the mean temp. So my question is, why don't you just put the mean temp immediately on normal distribution?
That could be a way. Yeah, I mean that could be a way. The question is like here, what you are saying is like you have this number, okay? This number reflects the accuracy of the sensor, okay? And this number reflects the variability of the temperature along the day. No, this is across the different days. This is like the variability of the mean temperature of each day across the different days. And within the same day, you can have different temperatures. And how much varies is reflected by this number. You have a much more grain control, okay? I mean, it's like you can just remove this guy and then you just assume that there is no variability across a single day. You can do this kind of simplifying assumption. That would be possible. Okay, perfect. But the next thing is like you can just explicitly do this this is like the box loop that we saw before. So your assumption is like there is no variability within the days. I remove this guy, I put here mean temp, and that's all. If your assumption, your knowledge, tells you like there is variability across the day, and we have to account from this variability because it may have a strong impact in the number of ice creams I sell, then you introduce it. Okay? Perfect? Yeah?
Variances, they are also re-estimated.
So, say again?
These variances
Yeah.
are also re-estimated
No.
Or they are
No. They are fixed.
They are fixed, so the model doesn't adapt them.
Exactly. No, I mean, this is like you put here a number, okay? So you're telling like this variance is equal to 2, okay? So my question is like, what if you don't know which is this variance? What would you do?
You have mean term.
Exactly. So if there is anything that you don't know, you define it as a random variable, okay? That's the trick, okay? Actually, this is what people do usually in these kind of cases, okay? But the nice thing is like, if you have this knowledge, you can go here specifically and input this knowledge. Because, it's explainable, it's like, yeah, we have full control, okay, in this example. Okay, so we are going to continue, and then it's like, the next thing is like the sales. Okay, so we are going to model the sales, the number of ice creams I sell, okay, at every moment in time, and then it's like, again, so I'm going to model the number of sales because it's an integer, okay, that takes positive numbers between 0 and infinite. Okay, I'm going to use a Poisson because it's a standard way to model variable that takes integer numbers, okay? And because, so the Poisson depends of something which is called like the rate, which defines the mean and the variance of the Poisson. So the rate now is going to be something which is going to depend of the temperature. Perfect? Yeah. This is probably very well easy to see here. So the sale depends on the temperature. So it's like the number of ice creams I sell at each moment in the day depends on the real temperature that there is at each moment in the day. Perfect? And this is like how we define it. And the question is like this linear relationship depends of 2 parameters, alpha, beta, okay, which are unknown. I don't know for each Celsius degree how many ice creams I sell, plus, the standard addition that they have. And because I don't know them, I define it like random variables again. Perfect? So it's like probabilistic modeling, where everything I don't know, I define it as a random variable, and everything I know, I also define it as a random variable, but these random variables are going to be observed, okay? These 2 guys are going to be observed, and all these other guys are not observed, okay? Perfect. And then the idea is like, I define my probabilistic model, I render it, I have a kind of, this kind of probabilistic graphical model, this kind of Bayesian network, I have here the distributions, okay, and then what I do is like, I just run inference, and then I query the posteriors, where the posterior is like, which is the temperature mean and which is the alpha beta values, which are the relevant values, because once I know the alpha beta values, I know the relationship between the sales and the temperature, okay? The sales, the number of ice creams I sell, depends on the temperature, multiplied by beta plus alpha, okay? Or more precisely, it's a random variable, a Poisson random variable whose rate is defined by this linear relationship which appears the temperature times beta plus alpha, okay? And the inference is going to give me, the posterior distribution. So 0.5 ice creams per Celsius degree, plus a base of 40 ice creams, okay? But the important thing is like the uncertainty I get about these numbers, about these parameters. So here I'm capturing the uncertainty, okay? Perfect. So let me see. So I'm going to continue, okay? And then I'm going to ask you, okay, to do the following exercise. So we have this model, okay? And now I'm going to ask you to do this exercise where the main idea of this exercise is like, I have the ice cream shop, and then I know that it's not only the temperature, it's also the humidity. It's also affecting the number of ice creams I sell. So my assumption is like, by knowing, taking into account the humidity, I can make better predictions about the ice creams I sell. And I'm going to assume that I have a sensor humidity, okay? A sensor for measuring the humidity at each moment in time. I'm going to record these measurements of humidity, okay? And I want to extend the previous model in order to account for the humidity, in order to account for the impact that the number of screens I sell, okay, have not only in relation to the temperature, but also in relation to the humidity. And the idea is like you're going to start from the previous model that I showed you before, and then you should add that, okay? Perfect. And let me see. It's important that you realize here, like the sales are going to be a random variable distributed for a Poisson distribution whose rate is defined now by alpha plus beta for the temperature plus, let's assume, I'm going to help you a bit, gamma time sensor humidity. Okay, perfect. So what is gamma? Gamma is going to be the coefficient, the number that affects, okay, that defines the relationship between sorry, okay, that's, sorry, the humidity, okay, not the sensor, the humidity. The sales are affected by the real humidity, not by the sensor measurements, okay? So the sales are affected by the real temperature times beta, a number I don't know, this is because I define it like a random variable, plus the humidity, the real humidity times gamma, okay? Which is another number I don't know. So gamma, what can I do with gamma if I don't know gamma? I can define it as a random variable. What about with the humidity? What can I do? Okay, perfect. So yeah, the idea is like now you are going to extend, improve this model, make it more rich, using the knowledge that you have about the specific problem. Okay, and then we are going to reason about. We are going to see, which is going to be the values of alpha, the values of beta, and the values of gamma, okay? Not the values, but the posterior, the densities, the distribution over these possible values, capturing the uncertainty, okay, that there is present, which is going to depend on the number of observations, is going to depend on the quality of the sensor measurements, okay? All this stuff. Perfect. So the idea is like you have now, I don't know, maybe like at least, until the end of the session, okay, everything included, break, to work on here, okay, perfect, and then we will be around, okay, but before that, it's clear what you have to do, okay, any questions? Yeah?
Here you're assuming that you have a linear relationship between the temperature, humidity, and the sales and the rest, but what if you don't know this relationship? What if it's not linear?
Exactly. This is an amazing question, and then the answer is going to be tomorrow. We will see. No. I'm joking. So let me see. Yes, exactly. Let me see. So, yeah, this is again like the box loop. Okay. So the idea is like we are going to see tomorrow, but the idea is like here is you can define like a function f. Okay, parameterized by some parameter theta, where J can be a neural network, and then theta are the parameters of the neural network, which are unknown, but can be defined using a random variable. Yeah. Everything is possible. Yeah. So yeah, no more time. Yeah. Okay. So please, if you have any specific question, just raise your hand, okay, and just keep working. So let me just end telling you something more. So it's like we are going to post the solution, okay? Perfect, the notebook with the solution. And there is also some extra exercise here when we work even being temporal, okay? But no time for that today, okay? Yeah. So, yeah. Okay, so yeah. So we are going to, let me see. I'm going to quickly go through the solution. Okay, perfect. So yeah, we don't have more time. So yeah. So let me see. So the first thing that we do here, and maybe I'm going to start by the end, okay? So now the sales, the number of ice creams I sell at every time of the day is going to be a random variable, okay? Perfect. Now this random variable is going to define by the rate, and now the rate, okay, is going to depends on the temperature times beta plus alpha plus this gamma times humidity, okay? Something that we just already discussed. What happened with the humidity? Humidity means like the real humidity, okay, at the current moment in time, which is a quantity that cannot be observed. And because it's not observed, it's modeled as a random variable, okay, humidity. And because it's a random variable, has a density, perfect, and this density means like, you know, how much the humidity varies across the day. Perfect? It's like a Gaussian, how much varies across the day. And, you know, so it's centered around the mean humidity of the day plus some variation, which is like, I can assume that is 2. Okay, perfect. Then mean humidity, you know, which is the mean humidity, is like I'm going to do the same like with the mean temperature by defining, again, as a random variable using the Pyro.sample construct, okay, and defining a normal distribution. Now, you know, because I assume that the mean humidity moves across the different days around like 80%, okay? Yeah. But the question is like, I cannot observe the mean humidity. I do observe a sensor measurement of the mean humidity, and this is what I also include here, okay? Another random variable, which is the sensor humidity, which is normally distributed around the humidity that there is in this moment in time, okay? It's just the same idea when this number reflects, in this case, the precision of the humidity sensor. Oh my God. Perfect. Any questions so far? Yeah? Sorry?
If you would comment the sensor humidity line, if you would comment it out,
Yeah.
and run the code, it still runs.
Yes, of course, it still runs. The problem is like, yeah, that's a good point. Yeah. The code is still run, but the question is like this random variable will not be observed. Sorry, no, I mean, sorry. I mean, it's like if you comment this out, no?
Yeah.
Perfect, exactly. So if you comment this out, means like you just remove this random variable.
But the real humidity is still used.
Yes, exactly. The real humidity is still used, but the problem is like you are not introducing information about the measurements of the real humidity.
What then happens to you?
Yeah. It's a nice question, a bit tricky. Okay, in reality, this variable will be like a latent factor. It's like something that is like, then you say like, the sales is like alpha, some base number of sales of ice creams, plus beta times the temperature, okay, plus gamma times some extra factor, yeah, which is not observed and doesn't have any relation to humidity. It's like some latent extra factor, okay? And then you enter in like kind of tricky issues because it cannot be really identifiable, has to be, I mean, yeah, probably in this case, probably doesn't really make anything, I would say, plus adding a bit of complexity, okay? Yeah.
How does Pyro use the sensor humidity?
Sorry, say again?
How does Pyro use the sensor humidity?
Yeah. Let me see. So the sensor humidity is a random variable, okay, that you define, okay, that follows this distribution, and is used to take into account this evidence that you have collected, these observations. Okay? This is what we do. Okay? So the name of sensor humidity, so here is a dictionary, then there is a name, and then this name matches the name of the random variable. So when I do the inference, what I'm saying to Pyro is like, it's like this random variable is replicated n times, 10 times, and the first instantiation of this random variable is observed with this value. The second instantiation of the random variable is observed with this other value, and so on. Perfect? Yeah. And then this information flows from here to here, from here to here, yeah. Perfect? So, yes, I think I have like time for 1-2 questions more, yeah, because we are running out of time. So say again?
The information flows from the sensor to the variable, right?
Yeah.
But the graph shows the opposite because mathematically it doesn't make a difference.
I mean, let me see. So now we go to this separation, okay? So it's like the information goes from this guy to this guy, okay? Because they are directly connected, okay? It goes from this guy to this guy to this guy through this guy because this guy is not observed, okay? But it goes from this guy to this guy and goes here. And because we have like a head arrow that is observed, it means like it goes from here and affect all these guys. Perfect. And actually also this guy and also this guy. Yeah. If you don't observe this guy, you don't have the number of cells, then the humidity is not going to tell you anything about the temperature. Okay, perfect. We are mixing different concepts here. Yeah. Let me see. So, yeah. So there is something more that, it's like an extra exercise for you guys, which is like, so what if we know that temperature from moment in time is close to the temperature in the next moment in time? So we know, like, if we are now like here, like 80 degrees, so we cannot be, like 5 degrees in a while. So it could be like smooth change, okay? So the temperature at the current time step depends on the temperature in the previous time step. Perfect? So we can encode this using temporal models, and that can be done in Pyro. And, we propose that as an exercise, and we will also provide the solution. But, yes, a lot of things to look at, and we didn't have the time. But, you have the material, and I think with the knowledge that we have today, it should be relatively easy for you, okay, to get it, okay? And that's all for today.